Every day in this unit so far, we have talked about light or electromagnetic radiation in a wave context. Refraction, diffraction, interference, polarization. Those are all properties of waves, and they're all properties that are exhibited by EMR. Therefore, EMR must be a wave. Well, guess what? We have evidence as well to support not the wave nature of light, but the particle nature of light. Today, I'm going to tell you a little bit about that particle nature of light. I'm not going to tell you about the evidence for the particle nature of light yet. You're going to have to trust me until tomorrow. But there is evidence to support the particle nature of light. Now, does that mean that we throw out everything that we've done so far? Not at all. Not at all. We still buy the whole wave theory of light, but now we also have the particle theory of light. So how can we reconcile the two? Well, in a way, it's almost a cop-out. It's almost a fence-sitting argument. Is it a wave? Is it a particle? Let's say it's both. It's a wave and a particle. In fact, we say for the last 100 years we say that light has a wave-particle duality. Light is both a wave and a particle. Sometimes it exhibits wave properties, and then sometimes it exhibits particle properties. But it has properties of both. You're going to learn a little bit later on about how the lines between waves and particles have really gotten blurry. Because not only does light behave like a wave and a particle, but things like electrons also have a particle and a wave nature. So now we're talking about wave-particle duality of pretty much everything. The line between a wave and a particle, which was, as of 5 minutes ago, very clear, is now getting a little bit blurrier and will continue to get a little bit blurrier as we progress here. Question? Yes, partly, yes. Yeah, I'm going to show you a video here in not next couple days, but here in the next week or so. I'm going to show you a video that demonstrates that. Man, nothing will blow your mind more than that 5-minute little video. You're going to watch that and you're going to think, oh, geez, I thought I was starting to understand stuff. You're going to go right back, further back than where you actually started. But the nice thing about that the evidence that we get from that is it's not so much that, oh man, I know less, like I'm screwed, I know less. It's an understanding that you can't know more, if that makes sense. So that's knowledge. That's an understanding that you can't know more. I shouldn't say that you can't understand, but that you can't know more. Yep.
Joke's on you, I'm so far back that you so that video I can't even go any further back. So I don't even understand that. So how do I understand that?
We'll see how that goes. Okay.
Could you say that light is just particles moving in like a wave?
No. What I want you to understand here, and we're getting a little bit ahead here with your questions. That's okay. What I want you to understand is that light does behave like a wave, absolutely. And light does behave like a particle, like a little pebble. When you throw a rock, that's like what we call a photon or a quantum of energy, okay, a little package of energy, bundle of energy. It's not little rocks like this moving on, kind of surfing on a wave. It is a rock moving this way, and it is a wave going like this. It's both of them. Now, how do you visualize that? Well, you can't really, because the problem is when you go to visualize it, you go to see it, you can't see both properties of it, the wave nature and the particle nature. It exhibits one property or the other at a given moment in time. So we can't visualize it because we've never seen with our eyes a wave and a particle at the same time. our model says that it's a wave and a particle at the same time, but we have no way to visualize something that's completely out of the realm of our experience. Peter? Does it have something to do with what? Pilot waves? I'm not sure what you're talking about. Yeah, I'm not sure. I'd have to watch that. I'd have to watch that video. Was it on YouTube? If you find it, send it to me again. If you find it again. Yep.
Is there a way to convert like a particle into a wave
Um,
or vice versa?
not well.
Like
No, not exactly. There's ways of making it exhibit wave properties, and there's ways of making it exhibit particle properties. But you're not converting a wave to a particle and a particle to a wave because it is a particle and a wave. It just exhibits one property or the other.
so it's both at the same time, but it only shows one at
Yeah, I guess you could say that, yeah. All right, so here's what we got, guys. Here's where we start off, at least here. A photon is a quantum of energy, a bundle of energy, a particle of light. It's like a rock being thrown. Now, it's still a wave as well, but I want you to picture it now not as the wave with electric field, magnetic field, although it does consist of that. I want you to picture it now as me throwing a bunch of pebbles or a bunch of erasers at somebody who happens to be sleeping on the back corner. Okay? That's a photon. That's a particle of light or a quantum of energy. Now, a photon, if we say it's a quantum of energy, it must be associated with a certain energy, right? And the energy that is associated with it is E. It's given by the equation H, which is foreign to you right now, but we'll explain that in a second, times C over lambda. Or we can make it H times F. C is the speed of light in a vacuum, 3 times 10 to the 8. Lambda is the wavelength. F is the frequency. The only thing we don't recognize here is H. H is a constant called Planck's constant. It's named after a guy named Max Planck, who was one of the originators of quantum theory, not of photon theory, but of quantum theory, from which photon theory developed. The value of Planck's constant, this is a little bit weird actually, 6.63 times 10 to the minus 34 joules seconds. But it's also got a 4.14 times 10 to the negative 15 electron volt seconds. How can it be two different values if it's a constant? Well, the speed limit on the highway from Okotoks out to Highway 2, the speed limit on Highway 2A is a constant 100 kilometers per hour. But you could also say it's a constant 62 miles per hour. How can we have two numbers? Well, because it's different units. We have two values of the constant simply because we have different units. Just like 62 miles an hour, 100 kilometers per hour, it's the same number, just different units. Christian? Yep. Energy of a photon. Now, remember when we did the spectrum and we identified the 7 different types of spectrum, we said you got to remember 7 different frequency ranges, although you really only have to remember 3 and then find the rest of them, right? 7 different wavelengths, although you can calculate frequency from wavelength using V is equal to F times lambda to compare them against frequencies. Remember we said you got to remember 7 different energies as well? We don't really need to remember 7 different energies. What you need to do in that case is take this equation, rearrange it to solve for F. Okay, the energy of the photon divided by Planck's constant gives you the frequency, and then you compare it against the known frequencies, those 3 ranges of frequencies that you memorized, compare it against your table. That make a little bit of sense? Last thing I'm going to say, guys, not going to do a problem here, but the last thing I'm going to say, which value of Planck's constant do you use? It depends. It depends. If your energy is in joules, what Planck's constant do you think you're going to use? The first one. If your energy is in electron volts, what Planck's constant are you going to use? Electron volts. Most times, it doesn't matter which one you use. There are a couple situations where you've got to use joules, and I'll make sure I point those out when we get to them. Okay?